present planar velocity estimation for fast-moving mobile robots using optical flow. Accurate velocity estimation is crucial for the safe operation of mobile robots, but common approaches based on proprioceptive sensors like wheel encoders frequently fail when the underlying assumptions like perfect traction don't hold. In such instances, the use of exteroceptive sensors like cameras would allow for velocity estimation without such stringent assumptions. A common approach, especially in the UAV domain, is to use cameras and do what is called visual inertial odometry. Hereby, landmarks are detected in the camera, which are then triangulated to determine the vehicle's pose. When this is done continuously, one can construct a graph of the vehicle's poses, and by taking into consideration the measurements of the inertial sensor, one can estimate the vehicle's velocity in 3 dimensions. However, most wheeled robots, especially autonomous cars, only move in 2 dimensions. For this reason, we present an approach where the camera is pointed downwards such that it sees the ground below the car. Looking at the ground is interesting because from the perspective of the camera, it can be considered a single rigid body that is also moving in 2 dimensions, but in exactly the opposite direction of the vehicle. From planar kinematics, we know that the motion of all 2D rigid bodies can be characterized by a single velocity and rotational speed. By estimating optical flow on the ground below the car, we are essentially computing the velocity at many different locations on the same rigid body. And by single value decomposition of the flow vectors, we determine the single rotational translation that describes the ground's motion in relation to the camera. Of course, the described camera configuration will lead to severe motion blur, as illustrated by this example of a fast rotating disk. And as we can see, this has an adverse effect on the optical flow estimation. Conversely, event cameras with their asynchronous and extremely high capture rate do not suffer from this problem. Event frames can be constructed by accumulating events over extremely short time periods to ensure sharp images even for very fast-moving scenery, and thus allowing accurate estimates of optical flow. Furthermore, through experiments conducted on a public highway, we demonstrate that it is possible to capture sufficiently sharp and feature-rich data that can be processed by off-the-shelf optical flow algorithms to compute high-quality flow estimates. Finally, we compare our approach against the state-of-the-art Event-VIO method using a Viken motion capture system. Our results show that measuring velocity directly from the optical flow on the ground outperforms VIO, especially for lateral velocity estimation, which is crucial for detecting unstable vehicle conditions such as tire slip.